Hi there. This video is going to record my attempt at the SACE Mathematical Methods written examination from 2022, starting off with question booklet 1. Looking at question 1 part A, we see some first principles. That's a little unusual to see so early in the paper, but it is a relatively straightforward question, so hopefully hasn't caused anyone too many problems. First up, we'll start by substituting f of x into the first principles formulation. Next, I'm going to expand and collect like terms. Now I'm going to take out h as a common factor of the numerator. With the common factor of h cancelled, the limit as h tends to 0 can be evaluated, giving us a function f-x equals 2x, which is what we'd expect to see. Part B of this question asks us to determine dy and dx for two functions, and in this case we don't need to simplify our answers, so just apply the laws of calculus as we see fit. First of all, it's probably worth noting this plus sign in between the two terms we see. That means that we won't be using the product rule, we will in fact be differentiating the first term, 3x to the power of 4, and then the second term using the chain rule. So, dy and dx will equal 12x to the power of 3 plus, and now the chain rule applied to this term will be 2 by 7 plus sine x to the power of 1 multiplied by the derivative of what's sitting inside that bracket, which is 7 plus sine x, which differentiates to 0, 7 differentiates to 0, and sine x differentiates to cos x, so it'll be multiplied by cos x. And that's our first one. Next up, we have a bit more of a complicated function. This one is a quotient rule in structure. And inside that quotient rule, we have an ln function and an e to the x function. So, I'm not going to try making up any log laws. There's no simplifications that are going to help me here. I'm just going to dive straight into using the quotient rule. So, the derivative of the top line, ln brackets x to the 5 plus 1, will be 5x to the 4 over x to the 5 plus 1 multiplied by the denominator, e to the x, minus the numerator, undifferentiated, times by the derivative of the denominator, which is also e to the x. And our quotient rule is finished off by e to the x all squared. And as I said before, no need to simplify, so we'll leave that as our final answer. Part C, using the laws that we know about integration, we can see that this integral will be the natural log of x minus 3 plus 4x, the integral of 4, plus c, the constant of integration. And we're not going to need to worry about using absolute value signs around the x take 3, because we can see that x take 3 will be positive because x is greater than 3. So that's question 1 all finished. Question 2. This question looks at the leading digits of numbers and a thing called Benford's law. Benford's law gives us a table here where the leading digit of a number, being the digits 1 to 9, occur with the probabilities that have been provided, and we note that those probabilities are not equal. The highest probability being for the leading digit of 1, decreasing as we move through from leading digit 1 to leading digit 9. This is an interesting piece of mathematics that we're touching on in this question. First of all, we're asked what property of these values in the table mean that x is not uniformly distributed, where x is the leading digit of a number. And I guess the simple observation here is that the probabilities are not equal, which would we expect to see if there was a uniform distribution. Now part B asks us to determine the probability of a randomly selected naturally occurring number having a leading digit of 6 or greater. And that requires us to add together 4 probabilities, something that I'm going to do on my Go's calculator. we can see that the answer is 0.222. Next up, part C asks us to identify which of these calculations would give us the mean of the leading digit, in other words, mu of x. And we're given some formulas that all look a bit familiar, but the formula we're looking for is the sum of x times by the probability of x, and that would be the second option provided, so I'm going to tick that middle box there. Now we're told a little bit about Benford's law and how it can be used to detect fraudulent financial transactions. The mean of the leading digit in a set of financial records is greater than 3.441. Now we're not told where that number comes from, but we're just given that as our sort of threshold for whether or not a set of financial records needs to be investigated further. And we're told that there's a sample that's been taken of 250 numbers from a record, and we have the mean of 3.816, which is of course greater than the 3.441, but the question is, will the confidence interval confirm the significance of that result? So we're going to calculate a 95% confidence interval. I'm going to do that on my graphics calculator in the statistics mode. So I'm going to move into menu 2, the statistics menu. I'm going to go to the interval section, do a Z interval using a single sample or one sample. And we can see this is already set to be a 95% interval, but my sigma value will have to be changed to the value provided, which was 2.462. And the x bar, the mean of the sample will be 3.816, and the sample size was 250. And we have our confidence interval there as between 3.51 and 4.12. Now the question is, does this confidence interval suggest that further investigation should be undertaken? And if we compare this confidence interval to the threshold for the mean of 3.441, we see that the entire interval lies wholly above 3.441. So in other words, our interval is telling us that the mean is somewhere greater than 3.441, and so that is the answer is yes, we should investigate these records further. Okay, now question 3. We're given a graph of a function f of x. We don't have an equation for this function. We're told we have two stationary points, A and C. We have a single inflection point at B. And also we have an asymptote with equation x equals 4. So all that information is provided in the graph. And now we're going to generate sign diagrams for f dashed x and also for f double dashed x. So first of all, we need to label the sign diagram for f dashed x with the critical values. Those critical values will when the derivative will be 0, which will be at the stationary point at A, which is value 1, or the stationary point at C, which is value 3, and I'm going to try and line those up nicely with the graph above. I'm also going to mark in the asymptote at 4. I'm going to put a couple of dashed lines there and mark in the asymptote at 4, but those are the critical values we're looking for. And now we need the values of positive and negative to indicate when the function is increasing and decreasing. Obviously increasing will be when the first derivative is positive, so that would be in between 0 and A will be positive. Then it is decreasing from A past B to C, so that's decreasing for that region from 1 to 3. Then increasing between 3 and 4. Then we have our discontinuity, our asymptote, and then it's increasing again beyond 4. So those are the signs we need to attach to that sign diagram. Next up, we're going to do the same bit of thinking around the second derivative, but this time the critical value will be at 2. Where the second derivative is 0 because there is an inflection point, and the other critical value will also be at 4. Once again, with the asymptote creating some discontinuity. You can see that's not quite on the screen there. Let me just slide that up a little further. So now the signs for this sign diagram for f double dashed x will be positive when the graph is convex or concave up, and negative when it is concave down or just concave. And that concave down region will be between 0 and B, so there's a negative sign to start off. Then between 2 and 4 it is convex, so that's going to be positive. And then the region past 4, once again it's concave, so that's a negative region there. So just make sure that you don't include any additional marks for the sign diagrams. We don't want to suggest any other critical features other than the ones we see there. Okay, with that bit of information done, that thinking done, we're now going to draw a possible sketch of f-x. Now, obviously the sign diagram that we've drawn can help us here a little bit. If we think a little bit about the inflection point, the first derivative will be at its most extreme value, in this case its least value, because that inflection point is pointing downwards, at x equals 2. So we're going to put our minimum here at 2. In this case I'm going to curve my function sort of parabola-like down to that minimum, back up through the intercept at 3. Now it's worth before I get too much further, there's an asymptote at 4, so our function can probably just head up in an asymptotic fashion that way. I'm going to call that the intercept at 1 intercept there, and in the region between 4 and beyond, it doesn't reach a stationary point, so I don't want to get anywhere near that x-axis or flatten out too much to suggest some more critical behavior. I think that captures all we know about the derivative f-x. Question 4 is about Ted's oat milk. Apparently the fat content of this oat milk is modeled with a normal distribution. First of all, we're going to do a normal distribution calculation of at least 2.8 grams of fat. In other words, probability that x is greater than 2.8. So I'm going to go to the statistics menu of my calculator. In fact, I'm still there. If I press exit out of this calculation a couple of times and move to my distribution menu, go to the normal distribution, choose NCD, and at least 2.8 grams means 2.8 grams or more, so the lower bound will be 2.8, the upper bound will be, I guess, a large number. I'm going to use 1 by 10 to the 99, a very large number, and the standard deviation is 0.35, we're told, and the mean is 2.7. The next calculation is the probability that fat will lie between 1 and 3 grams, also a normal distribution calculation. So exiting it out of here, moving up, we can change our lower bound to 1 and our upper bound to 3, and executing that command we get 0.804. Now we're talking about Ted's oat milk being sold in packs of 6 cartons, and S6 representing the distribution of fat content in a 6-pack of Ted's oat milk. And we're asked to explain why S6 can be modeled by normal distribution. And my answer would be that as the fat content of the individual cartons is normally distributed, the distribution of sample sums of any size, including 6, will be also normally distributed. B part 2 says that we need to show what the mean and standard deviation of S6 will be. The mean of S6 will be 6 times 2.7, and the standard deviation will be equal to the square root of the sample size, so square root 6 multiplied by the standard deviation of the single serve, so that's 0.35. Even though I'm pretty sure those are going to be the values provided, I'm going to double check by checking that on my calculator. So B part 3, now we're going to determine the probability that a 6-pack contains less than 18 grams of fat. That would be a normal distribution calculation once again, but with a new mean and a new standard deviation. So we're going to move back to the statistics menu, back to the distribution, normal, have the normal cumulative, getting good work out here, and we want a less than 18 grams of fat, so we need a calculation that has a lower bound of negative infinity or something in that direction, and an upper bound of 18. But we're going to use the standard deviation that we've just recently calculated, 0.857 from the previous page, and the mean would be 16.2. So we have a probability there of 0.982. Part C asks us to find a value of k associated with the standard normal distribution z, and in fact is asking us to find the value of k such that the probability of z less than k is equal to 0.99. This can be done on the inverse normal menu of our calculator. So if we exit out of here a couple of times, and then back into distribution, back into normal, and choose the inverse normal calculation, we need a left tail calculation, so that's my calculator currently set to that. We want the area to be 0.99, and the mean is 1, and the standard deviation is 0 for the standard normal. And so that z score would be k equals 2.326. Now we have some information about the 6-pack of Ted's oat milk that discusses a claim that each pack of 6 contains less than 18 grams of fat, and the truth of this statement they would like to be 99% true here. So in other words, this statement needs to be true for 99% of the packages. Based on our calculations to B part 3, currently it is true for 98.2%, so not quite true for 99%. And so they are trying to improve the manufacturing process, and we're told that the standard deviation can be reduced. So the mean cannot be changed, but the standard deviation can be changed, and that means that we're going to have a situation with an unknown standard deviation but a known mean. And obviously this relates a little bit to part C with that z-score calculation of 2.326. That's going to come in very handy for this. So we're now asked to find the standard deviation sigma S6 that will result in this 99% of packs containing 18 grams of fat. In other words, we're using our z-score formula, z equals x minus mu on sigma. So I'm going to write that down with values included. So our z-score 2.326 equal to the x score of 18 minus the mean of 16.2 divided by our unknown value sigma. That means that sigma will equal 1.8, which is 18 minus 16.2, divided by 2.326. A quick calculation to be done there in run mode. So over there now, we're going to need 1.8 divided by 2.326. So that would be a value of 0.774 to 3 significant figures. Question 5. Now we have a function f of x cosine of our fifth x squared take 1. So a bit of an interesting combination of a polynomial and a trig function here. And here's a graph of f of x with two stationary points, one at x equals 0, one at x equals a, some point a between 0 and pi. First of all, we're going to start by stating the nature of the stationary point located at A, maxima, or you probably could say a local maxima. Next up, we're going to find f dashed x, so it's going to be a chain rule differentiation. The derivative of the outer function cosine x will be equal to minus sine of 1/5 x squared take 1, and multiply that by the derivative of the inner function, and that will be a fifth multiplied by 2x. And that's, with that simplification, that's the function we're going to be working with. In B part 2, we're going to use an algebraic approach to determine the exact value of that a. I'm going to move straight to the classic set derivative to 0 and then solve the resulting equation. So we'll start with that derivative equals to 0. I just cleaned up this a little bit. So that means that the sine term must be the one that's equal to 0, because we know that a is not 0, that's the other stationary point. That means we're looking for the solution sine something equals to 0. That will be true at 0. So that means the 1/5 x squared minus 1 equals to 0. It's also true if you consider multiples of pi added on to that, but because we're looking for the smallest possible value, we're probably not going to worry about that. So the smallest value that we're looking for here will be just rearranging that equation for x, and that will be x is equal to, if we bring the 1 across, times by 5, and then we take the square root of that. We want the positive square root because a is a value greater than 0. And now we have a exact boundary for the interval for which f of x is increasing between 0 and root 5. Now we're asked about the regions where f of x is decreasing most rapidly. So we're told it has no inflection points to the right of x equals a, and we're looking for the pointer points where it's decreasing most rapidly. I'm going to have a look back at my graph, and we can see that it is decreasing for this region through here. And it's decreasing with greater and greater magnitude, so I think the point where it's decreasing most rapidly will be at the end point, which is x equals pi. So that would be my answer to part 4. Brings me to question 6, which is the last question of this booklet. This is a question where we're doing a processing of medical samples in a laboratory. The arrival rate of these samples is given by this function m of t equals 500 t root t e to the negative 0.9 t. And first of all, we're asked for a function m dashed, which is the derivative of this rate function. So I'm going to do this by tackling this using the product rule. You might want to start off by saying the function is equal to 500 t to the 3 over 2 e to the minus 0.9 t, just to make it a little bit easier to think about that product function. M dash t will be equal 500 times by 3 over 2 times by t to the 1 over 2, now going down by 1 there, times by e to the negative 0.9 t, plus, because we're using the product rule, 500 t to the 3 over 2 multiplied by the derivative of that exponential term, which will be minus 0.9 e to the minus 0.9 t. Now, a little bit of cleaning up to be done here. 3 over 2 times 500 is equal to 750. We can sort of see that from the value that's been given, but it's worth double checking. T to the half is root t, e to the minus 0.9 t. So all we're really doing here is writing down what's above. But checking as we go, 500 multiplied by negative 0.9 will be negative 450. And that t to the 3 over 2 can be rewritten as t root t, as it was before, e to the minus 0.9 t. So obviously we're not going to get any marks for that line. We're going to get our marks for the first line previous to it. Okay, so now we're asked to use an algebraic approach once more to show that the rate at which medical samples arrive is maximized at t equals 5 on 3 according to the model. And so a maximum value will be found when we consider m dash t equals to 0, and that will be when the derivative is equal to 0. And I'm going to do a little crafty time saver here by taking out a common factor, root t e to the minus 0.9 t, and what remains in the derivative is 750 minus 450t. We can see that one of the solutions there will be 0, so we can have t equals 0 from the first term, or from the second term we can see that t equals 750 divided by 450. Solving that linear here equals to 0, and that equals 5 on 3. So that's not quite enough for the job to be done. We found when the derivative is 0, m dash t is equal to 0, but not when it is maximized. So I'm going to draw a sign diagram. And I know that it's 0 at 0. I know I have an endpoint at 9, because the function ends at 9, and I have a value here at 5 over 3. Now, whether it's a maximum or minimum, or indeed a inflection point of some description, will depend on the signs. I probably could do a test substituting in, for example, t equals 1 and determining the signs positive and negative. But I note that on the following page there's actually a graph. So I can see a graph and I can see that it's increasing before this this 5/3 value, and then it's decreasing afterwards. So I'm happy to put the signs positive and negative based on that graph, which is confirming that the exact time is 5/3 and the behavior is exactly that. Now we have to do a calculation of an overestimate. We're using rectangles to overestimate the value of n, which is the number of samples, the area beneath the curve, the rate curve. So we're going to do this calculation, and we're going to need some function values, and I'm going to in fact do this by drawing the graph of m of t, and I'm going to use that to get some values here because it's going to be useful later in the question as well. So I'm going to move to graph mode now and enter my function. So there's my function as given to me in the question, and I'm going to set my view window, and my x scale is 0 to 9, and the y scale hasn't been provided to me. I can't see that on the graph. I'm just going to leave that, draw my graph, and see that obviously that doesn't look great. My y scale will need to be changed, but I'm going to use zoom auto, so press F2 and then F5 to automatically zoom the y scale to fit my x scale, which is a nice little trick there. And now I've got myself a graph, very much like the one provided in part B. So, the value of this overestimate, well, the widths of these rectangles are 3. So it's going to be 3 multiplied by the heights. So the heights are going to be, first of all, we're going to need the height of this maximum point. We can see that first rectangle, its endpoint is not at the boundary 0 or 3, but in fact at the maximum. So we can go that by going gsolve and max, and we can see the height there is 240.0. And now my next rectangle height will be at 3. So now I'm going to use trace, press shift and F1, and I'm going to jump to 3 just by pressing 3. And my height there is 174.6. And my last rectangle will be 3 multiplied by the function height at 6, so just press 6 and hop there. That looks like 33.19. Now to evaluate that, I'm going to have to jump back into run mode. I'm going to use 3 multiplied by all of the things combined. $1,343. Part 2 asks us to increase the number of rectangles. If we did increase the number of rectangles, we would approach a value n. That obviously will be the exact area beneath the curve, which we could find using, definite integrals. I'm just going to use my graph that I grew before. Back to menu, back to the graph mode. And for this one, I'm going to go to the gsolve menu, pressing F5, around the corner, the definite integral menu, and I'm going to do a simple calculation here. I'm going to go from the integral from 0 up to 9. That's the domain we're looking at. And that value is 859.5, so to the nearest whole integer, 860. Now we're told that the processing of these samples takes place in a queue, and the processing takes place at a rate of 150 samples per hour, and I think that's been represented by that horizontal line there. And we can see that it intersects a couple of points here. So for a while the rate is above the arrivals, the rate of processing is above, then for a period of time the arrival rate exceeds the processing rate and then drops below it again. So that is fairly important information to get our head around the idea that obviously they're coming in slowly, then quickly, then slowly, but they're chugging away and processing the queue as we go. And we're also given this important bit of information that it starts off with 600 tests in the queue. So even though there aren't many arriving first thing in the morning, they can start processing straight away. So first of all, we're asked to explain why the number of items in the queue is decreasing until a certain period of time, and that is because the rate of processing is greater than the rate of arrival. So C part 2 says that during the time the items of the queue is increasing, the queue increases by k samples, and we need to find k using an integral expression from 0.67, the first intersection point, to 3.36 of m of t minus p of t dt. And that essentially is finding this area here, which is the amount by which the arrivals exceed the processing between those two periods of time, 0.67 and 3.36. Now, hence or otherwise, we're going to find that value of k. I'm not sure what the otherwise would be, but I'm going to do this. And in fact, I'm going to use the run mode of my calculator now to do the remainder of this question. So in run mode, I'm going to go to Math and round the corner to find that definite integral symbol. And I'm going to do the definite integral between the function and the line 150. So the function is actually stored in my calculator. Rather than re-entering it, I'm going to call it up using its name. It's named y1. So I press vars and graph, get the y from there, and it's y1 minus the function 150. No need to enter that in any complicated way. And the boundaries here were 0.67 and 3.36. And that gives us our calculation of 152 to the nearest integer. Now, the last calculation for this question, in fact for this booklet, is to determine the number of medical samples in the queue at 5 p.m. Well, the thing to remember here is that there's that number 600, which is where the queue starts, and then to that queue is added the amount that is arriving, so that's the integral from 0 to 9, and that's the amount arriving, m of t, minus the number processed, which is 150. And that's the calculation that will give us the number in this queue at the end of the day. I can get that by editing my command above. So I'm just going to come back into it, pop him back down this end and put in that 600 and the plus sign, and then move down to the bounds, and I want 0 and I want 9 on my bounds. 9 there, so that's going to give us 109.5, so 110 to the nearest integer. And that's the finale for that question. So I'm going to have a break now, and then I'll get stuck into book 2